Okay, today we're going to talk about Chapter 2, beginning Chapter 2, which is on limits and continuity. We'll get into a little bit more of continuity later on, but uh, really to understand what a limit is, you have to talk about continuity a little bit as well as we go, but there will be a separate section on continuity coming up. Section 1A, though, is on limits and continuity. So the first thing we're going to do is just do some simple limits. The very first thing that you want to do when you're trying to take a limit is simply to substitute the value in. So on these first few examples here, it asks you to take the limit as x approaches 2. That's how we read this. The limit as x approaches 2 of 2x. And really, we can simply just plug 2 in, and we get 2 times 2, which is 4. Okay, that will be this limit. So many times, just plugging in the value will give you the limit. If you plug in -1 into this second example here, b, you get -1 plus 3 over -1 squared plus 3 times -1 plus 1. So on top we get a 2. On the bottom we get a 1 minus a 3 plus a 1, which will be across the bottom will be a -1. So 2 divided by -1 will be -2. Your limit will be -2. What does that mean, though? What does it mean when we have a limit of these values? Let's take a look at what these would look like in the graphing calculator. So if we graph, for a here, we graph 2x. If we graph the function y equals 2x, make sure you're in function mode again now. We're not in parametric mode. And if we graph this, I'll go zoom 4, to graph it, we get a line that looks like this. And if we take the limit, again, for this particular problem, you were taking the limit as x approaches 2. Okay? And we said that the limit as x approaches 2 was 4. Well, if we come back to this, I'm going to change the zoom here. I'm going to go zoom 6 so we can see a little bit more of this graph. But the whole idea of that is, and I won't be able to draw necessarily on here, but if you approach 2 from the left, this arrow right here gets closer and closer and closer to 2 from the left, and as I approach 2 from the right, I get closer and closer and closer to 2 from the right, the y value is getting closer and closer and closer to 4. I will say the words closer and closer and closer a lot in this section and in this chapter, to the point where it gets a bit annoying. But that's essentially what you're doing when you're taking a limit. Unlike almost anything else in mathematics, where math teachers want the exact amount, limits, we want to know what happens when you get really, really, really close to it. Now, in this particular example, the value of the function itself is also 4, but that doesn't matter when we're taking the limit. It's nice if the value of the limit equals the value of the function. We find out that that will make the function continuous at that point. That's where the term continuity will come in. But we must understand what a limit is before we can truly understand continuity. It's a hierarchy. You have to have a limit before you can have continuity. You have to have continuity before you can have differentiability. So everything we do is going to be building one on top of the other so that we can understand what all of these concepts mean. Let's go back to the lesson then. We could even look at the same thing, this x plus 3 over x squared plus 3x plus 1. If we type that into the calculator. Now, it's a rational function, so we don't know for sure exactly what this is going to look like when we graph it. If we could factor the bottom, we could find the asymptotes, but it's not nicely factorable. But let's just type it in and take a look. If we clear this out, and we go parentheses x plus 3. Got a cursor back here. Parentheses x plus 3. Close the parentheses. Divided by parentheses for the bottom. X squared plus 3x plus 1. And we graph it. So now if we go zoom 6, here comes this picture. and we want to take the limit as x approaches -1. So if you look at this picture, maybe a zoom 4 would be better here. Notice that this is a rational function. It has two vertical asymptotes that you can see here. But as we approach -1, this y value here is approaching a certain value. Okay? And as we approach -1 from the left, it's approaching a certain value. And through taking this limit, if we go back and we look, that limit happens to be -2. The value that it's approaching from the left and from the right is -2. So when you're taking a limit, and you're looking at it graphically, that's what you're looking for. You're looking for what is the value that you're approaching, what y value are you approaching as x approaches a certain value from the left and from the right. If you look at something like this, it says explain why substitution does not work to find the limit, and then find the limits if they exist. On these two examples, neither one of them will work. If you just try to do substitution here, you get the square root of -4. Since the square root of a negative number is undefined, substitution will not work. Okay? Likewise, in this case, there is no limit, by the way. And there are many times where there is no limit on a variety of different functions. If you take a look at this particular situation, if you plug it in, you get 0 over 0. The problem here is substitution won't work because of the 0 in the denominator. Since there is a 0 in the denominator, substitution, run out of room there, will not work. Okay? And in this case, again, you do not have a limit, but this is an interesting problem. With this first one, it's just not defined. It's not defined anywhere to the left of 2 because the domain here is x is greater than or equal to 2 on this example here. But on this second example here, it's not defined at 0, but we certainly can approach 0 from the left and from the right. Let's take a look at this one graphically and see that, again, this is going to be no limit. But why is it that there is no limit? If we take a look at the graph of this particular situation, y equals, we'll clear this out. We're going to go math over the number ABS of x, cursor to the right, divided by x. Hit enter. And we're going to go zoom 4 for zoom decimal. If we look at this particular situation, watch. As x approaches 0 from the left, the y value gets closer and closer and closer to -1. As x approaches 0 from the right, the y value gets closer and closer and closer to +1. Since the left-hand limit does not equal the right-hand limit, we have no limit. They have to approach the same value. If we come back to this situation right here, okay, the left-hand limit would be -1, the right-hand limit would be +1. That's why there's no limit. Let's take a look at the next example. When we want to take the limit of many rational functions, if we take a look at this, if we plug 1 in to this equation, we get 1 minus 1 over 1 minus 1, which is 0 over 0. Now, we just looked at a 0 over 0 situation in which there is no limit. But the fact is, the vast majority of cases where we get 0 over 0, we will be able to find the limit. So in most cases, when you get a 0 over 0, you can still take the limit. Here's what happens in this particular situation. We can factor the top, or factor the bottom, to be x plus 1 times x minus 1. And after we factor, we can cancel. And so now we're simply taking the limit, and you must write this down every time as you're simplifying limits. The limit as x approaches a value. Do not simplify and simply eliminate the limit as x approaches the number portion. You stop writing that down when you plug 1 in. Now we're done simplifying. When we plug 1 in to take the limit, we get 1/2. This has a limit of 1/2. How can that be? How can it have a limit of 1/2? Well, the key is this repeated factor that appears in the top and the bottom. And we should know from graphing situations like this in the past that that creates a hole. And we have a more technical name for a hole now that we're in calculus. It's called a removable discontinuity. So let's take a look at this x minus 1 over x squared minus 1 function. If we clear this out, parentheses, x minus 1, close it, divided by, parentheses, x squared minus 1, close it. And I'm going to go zoom 4 because you're going to see it a lot better with the zoom decimal. This happens to be a rational function. When we reduced it, we still had a rational function. It has a vertical asymptote at -1, which we can clearly see right here is the vertical asymptote. But at the same time, look at, there's a removable discontinuity right here. But as x approaches 1 from the left and as x approaches 1 from the right, both the left hand and the right hand limits are approaching this value of 1. Okay? And so when we come back to this situation, approaching the value of 1/2, I should say, they're both approaching the value of 1/2. And that's why the limiting value is 1/2. It's essentially the y value where that hole occurs when we're finding the limit like this. So let's take a look at the second one, B here. The first thing you definitely want to do is type in, is actually try substitution. Because if we get a number out, that's the limit. We don't have to simplify. But if we look here on top, we end up getting a 0. On bottom, we get a 0. Most of the time, when you get 0 over 0, we can reduce and take the limit. Don't forget to write the limit as x approaches the number down every time as you simplify. This is t minus 2 times t minus 1 all over t minus 1 times t plus 1. Factor the top, factor the bottom, and cancel. The limit as x approaches 0 of t minus 2 over t plus 1. Now when you plug 0 in, you get -2 over 1, which is -2 back out. Let's take a look at this one graphically and see if we really are approaching the value of -2 as x approaches 1 from both sides. So we'll type this in. Clear the history here so we can see it better. Clear this out. Parentheses. X squared minus 3x plus 2, close the parentheses, divided by parentheses x squared minus 1, close the parentheses, And again, the best zoom is zoom 4 because it will actually show you the removable discontinuity in most cases. Type this in right. Okay. As we approach 1 from the left and 1 from the right, it doesn't look like it's approaching what we said. It looks like it's approaching a negative situation. Let's go back and see what we had. Okay. We said -2. But when you plug in, first of all, this is the limit as t approaches 1. That would be part of the problem here. As the limit as t approaches 1. So when you plug 1 in, sorry about that, 1 minus 2 over 1 plus 1 is -1/2. Good thing we checked it graphically because it was incorrect. Let's go back now to the picture. We can see that as we approach 1 from the left, the y value approaches -1/2. As we approach 1 from the right, the y value approaches -1/2. Okay? So when we're doing these problems, that's what we're looking for. Let's take a look at a couple more like this. Many of the problems in your homework will be along this line. You should always try, when you're taking a limit, just to do substitution. But if you plug substitution in, if you just plug 2 in to this example, example C, you get 4 minus 4 on top, which is 0. On the bottom, you get 8 minus 8, which is 0. When you get 0 over 0, look to factor. Or I should say, look to simplify. It's not always factorization. In this case, though, it does turn out to be a factorization. Factor out a 2, there's an x minus 2. Factor out an x squared, there's an x minus 2. Cancel. The limit as x approaches 2 of 2 over x squared. You have to make sure that you continue that correctly. Plug 2 in, 2 over 2 squared is 2 over 4, or 1/2. Again, we could go check this one in the calculator and see that it approaches 1/2 from the left and from the right. Let's try D. If you plug 0 in, you get 1/2 minus 1/2 over 0, which is 0 over 0. This one, though, is not factorable. It's not a factorable situation. There must be another way to simplify. There is one like this on a test or quiz in the future. So make sure you know how to do it. Again, it's all about getting common denominators. Multiply this fraction by 2 over 2, this fraction by 2 plus x over 2 plus x. When you do that, you're going to get a 2 minus a 2 plus x all over 2 times a 2 plus x. And right now, that's all over x. But when you flip, this x is going to end up on the bottom. So let's distribute the negative sign here. We're going to get 2 minus 2 minus x. When we multiply by the reciprocal, there's the big divider, we get x down here. That's what it's going to look like. Cancel. Never cancel terms and factors in the same step. Cancel. Plug 0 in. And you get -1/4. There it is. That's the limit. It's tough to graph that particular one, especially on this smart view. It's tough to get all the buttons typed in, but you can check it out and see that you just get a removable discontinuity at the point 0, -1/4. Okay, let's take a look at a few other things that will show up on this. One of the things that they do want you to do in this particular section is to look at the limits as you approach from the left and from the right. That's what they're doing here on this particular example. It says investigate the limit as x approaches 0 of the function f of x by making a table of values. So I've set up the table here for you in your notes. Here is the function right here. This is what they want us to type in. So here's what you would do. It's x. Let's type this function in. Clear this out. The function is x sine of 1 divided by x and we can graph this thing. Zoom 7 is a nice zoom for trig because it's zoom trig. All of a sudden we get around this x-axis here and it looks like it just kind of drops down and back. Let's zoom in once. If we go zoom 2 for in on 0, 0, watch what happens as we get close to the x-axis. We get close to the origin here. That's interesting. Let's do it again. Zoom 2 for in. Hit enter. Well, we keep getting this oscillating back and forth. You could do it again, and it's even worse. Well, let's take a look and see what's actually happening when we look at a table of values. So we're going to go second, quit. And the bad part about the table is you can't get it to scale the way that it wants. We just have to call it up. We're going to go vars, over to yvars, function, y1, and we're going to evaluate this thing at 0.1. And we get that for a value. Negative 0.0544021111. Now, the bad part is you're going to have to write all of this down in your chart. I'm not going to write these numbers down as we go, but you got to write all the decimals down because watch what happens here. If I call that up again, if I go second, enter, and I come back and I change this to 0, 1, close it, you get that. And you're going to write that value down. Then I'm going to go second, enter, another 0 and a 1. And hit enter. There's so many zeros here, it just goes to scientific notation, but this is 0.000082. So you definitely want to put this number, 0.00008, in to the table on the other page. If we do the same thing, it looks like it's getting closer and closer and closer to 0. If we do the same thing with the other side, now we can do this pretty easily by going second, enter, again, coming back here, putting in a negative sign, and going 0.1. Close it, hit enter. We get the same value that we plugged in when we plugged in positive 0.1. Second, enter, plug in 0, 1 here. And the whole idea is this is an exercise in getting closer and closer and closer to 0, both from the right and from the left. And you're going to put these numbers in the table. You need to have all of the numbers written out. And you'll have one like this in your homework, and we get the same thing. Notice how we're getting the same values out when we approach from the right and from the left, and that's because this happens to be an even function, and we're checking it as we approach 0. That will not always be the case. It's just in this particular situation because we have an even function, and we're approaching 0 from the right and from the left. But the bottom line is we see that this limit, as x approaches 0 of this function, approaches 0. For your notes now, make sure that you're filling this chart in with the numbers that we just took a look at. And you'll have one like that in your homework. I want to make sure that you saw that as well. Okay, example number 6. On this particular problem, the picture will be given to you in the book. It's not presented right here. I will draw it in for you so you can see what it is that we're going to reference. Here is the picture that we're going to be referencing. If you take a look at it, first of all, notice that there's an open circle at the point 0, 0. And that point has been removed and placed right here at the point. It's been replaced at the point 0, 1. Likewise, there's an open circle at the point 1, 1. And it jumps down here at 1 and has a value at 1 of 0. And it stays on that x-axis, so it continues to be 0 all the way over to 2. So that's what we're looking at when we look at this particular picture. Okay? All right. So it's going to ask a series of questions that want you to say which ones are true and which ones are false. The key is, when you're looking at these problems, I talked earlier about the limit as you approach from the right or the limit as you approach from the left. That is indicated by this little superscripted plus here, up here. Okay? And likewise by this little superscripted minus. It does not mean -1, positive. It means -1 from the right. So this first thing is saying, find the limit as x approaches -1 from the right. And that means we're getting closer and closer and closer to -1 from the right-hand side. So as I look at this picture, it's like I'm on the curve and I'm getting closer and closer and closer to -1. But from the right, I'm coming from the right. And the y value is getting closer and closer and closer to 1. So that is true. The second question here, B, says the limit as x approaches 0 from the left. You're getting closer and closer and closer and closer to 0 from the left. The y value is getting closer and closer and closer to 0. It is true. The limit as x approaches 0 from the left equals 1. No, we just said the limit as x approaches 0 from the left is 0. The value of the function at 0 is 1, but it doesn't matter what the value of the function is. It matters what we get closer and closer and closer to. So this is false. Does the limit as x approaches 0 from the left equal the limit as x approaches 0 from the right? Well, let's see. As we approach 0 from the right, get closer and closer and closer to 0. The y value is indeed getting closer and closer and closer to 0 as well. So yes, the left-hand limit does equal the right-hand limit. That is true. Okay. E then says, does the limit as x approaches 0 exist? Well, if the left-hand limit equals the right-hand limit, then we have a limit. I know. I wish that sometimes I use different words, but that's the way it's phrased. If the left-hand limit equals the right-hand limit, then we have a limit. So there's left-hand limits, there's right-hand limits, and actual limits. And if the left-hand limit equals the right-hand limit, it does indeed exist. That's true. And if the left-hand limit equals the right-hand limit, then that is your limit. So the limit as x approaches 0 of fx equals 0 is true as well. Then it asks, does the limit as x approach 0 of fx equal 1? No, we just said it equals 0. This is false. It doesn't matter that the value of the function at 0 is 1. Yes, f of 0 equals 1, but the value of the function does not determine the value of the limit. The limit as x approaches 1 of f of x equals 1. Well, that's not true. As we approach 1 from the left, it equals 1. But as we approach 1 from the right, it equals 0. The left-hand limit doesn't equal the right-hand limit. There is no limit as x approaches 1. So this is false. Does the limit as x approach 1 of f of x equals 0? No. If we wanted to make h true, all we would have to do is put a little superscripted negative sign behind the 1, and then it would be true. If we wanted to make I true, all we would have to do is put a little superscripted plus behind the 1, and it would make it true. Because the right-hand limit equals 0, and the left-hand limit as we approach 1 equals 1. But we do not have a limit. The limit as x approaches 2 from the left of this function equals 2. No, as we get closer and closer and closer to 2 from the left, the y value is getting closer and closer and closer to 0. So this is false as well. I took this. I know that the order of these questions might seem a little silly, but I took exactly verbatim out of the book, and you're going to have one that looks just like it. Make sure you know how to tell the difference between a left-hand limit, a right-hand limit, and an actual limit. All right, let's take a look at these last two examples here then. We're graphing piecewise functions and then looking at the limits. So again, when you graph a piecewise function, the biggest part about this is, again, we're not supposed to plug 2 into this top piece, but we have to plug it in to know that it's at the point 2, 1 is where that top piece is starting. Now it has a slope of up 1, back 1, up 1, back 1. There it is. This second piece, I'll do it in blue. Okay? I still need to plug 2 into it. When I plug 2 into it, 2 divided by 2 is 1, plus 1 is 2. This first piece is wrong. When I plug, let's do this in red. When I plug 2 in, 3 minus 2 is 1. So when I go to the right 2, I go up 1. It's that hole right there, right now. And then I'm going to go back 1, up 1, back 1, up 1, back 1, up 1, graph that out. The second piece I'll do in blue. When I plug 2 in to this piece, it doesn't start at 1, it jumps up here. And now it's got a slope of up 1 over 2, up 1 over 2, up 1 over 2, and we graph that. This is a picture of that piecewise function. It says, find the limit as x approaches 2 from the right. The limit as x approaches 2 from the right. I'm following down this blue line here. I'm getting closer and closer and closer and closer and closer to 2 from the right. The y value is getting closer and closer and closer to 2. So the limit as x approaches 2 from the right of this function is 2. However, the limit as x approaches 2 from the left of this function, I'm getting closer and closer and closer and closer to 2 from the left. The y value is getting closer and closer and closer to 1. Since the left-hand limit does not equal the right-hand limit, there is no limit. So the limit as x approaches 2 of this function is, you can write DNE for does not exist. It's acceptable on the AP test as well. Does not exist. And it's since the limit as x approaches 2 from the right of f of x does not equal the limit as x approaches 2 from the left of f of x. If they are not equal, then there is no limit. Last example, and then I'll put the assignment up. Here's another piecewise function. Let f of x equal, first of all, it's a rational function. Okay, so it has a vertical asymptote at 1. I'll dot that in momentarily. We couldn't plug 1 into this anyways, but if we were to plug 0 in, you would get out -1. If you were to plug in -1, you'd get out -1/2, because it approaches this horizontal asymptote of y equals 0. So it's going to look something like this. Okay, it goes through the point 0, -1, and then it comes down this way. That's that half of the rational function. It's hard to get a great picture on this because of the way it's oriented. Then it stops being that, and it becomes this cubic function. If we plug 1 into the cubic function, we get 1 minus 2, which is -1, plus 5, which is 4. So 1, 2, 3, 4. It starts right here, and this cubic function just takes off like that. Okay? That's what the piecewise function looks like here. It's one I took right out of the book. It's kind of a silly piecewise function, but that's the way it looks like. That's the way it looks. The limit as x approaches +1 from the left of this function, As we approach 1 from the left, it's this red function. As it gets closer and closer and closer to 1, the y value just keeps getting larger and larger and larger in the negative direction. It approaches negative infinity. The limit as x approaches 1 from the right of this function, as x approaches 1 from the right, coming down this blue function, it's getting closer and closer and closer to a y value of 4. So, do we have a limit? No. The limit as x approaches 1 of this function equals does not exist. And again, we can say, since the limit as x approaches 1 from the right of f of x does not equal the limit as x approaches 1 from the left of f of x. That's how you would say it. Okay? They are not equal. If the left-hand limit doesn't equal the right-hand limit, you do not have a limit. If the left-hand limit equals the right-hand limit, then that is your limit. Here's the assignment. Work on some of these tonight. We'll talk about this tomorrow in class.